Okay, can you hear me now? Okay, thank you. Thank you for confirming. Thank you. Thank you. Okay, so let me uh start sharing again. Okay, and let me just confirm recording is in progress, right? Yeah. Okay. Okay. So if you didn't hear me, then let me start all over again. So basically, I just wanted to welcome you to the course, which is about assembly language and machine organization. Uh, uh, Today we are not going to cover uh, any main or core content of the course. The purpose is only to introduce myself and to introduce the course and logistics about how we'll be conducting this course in this semester. Uh, So first, little bit information about myself. As you know, most probably, I am an assistant professor in the computer science department of NMSU. Uh, you can reach me through my official email, which is num@nmsu.edu. Right now, I am not in Las Cruces. That's why this course is conducted in hybrid mode. However, once I'm there, then my office or my room number will be SH170. But definitely, I will let you know once I am back to Las Cruces, if that happens to be the case. Uh, little bit background about my education. So I got my PhD in 2019, master's in 2011, and a BSc back in 2006. So it's been like quite a while. Uh, my research interests are computer architecture, persistent memory, focusing on the aspects like system software, hardware support, and security of the persistent memory. Then new concept, relatively new concept related to storing the persistent data on distributed memory in a reliable way, which is known as distributed persistency. So that is also an area in which I am currently working. And another area which I'm currently exploring is trusted execution environment. Uh, so as you can see, like these are like three, four areas, different but also related with each other. So at a higher level, if I want to simply give you a picture of what I'm doing, so my research is related to three different layers like operating system, computer architecture, and little bit work related to applications as well. So uh, right now, as I said, I'm working at NMSU since fall 2024. And prior to that, I was a postdoc research scholar at University of Central Florida in Orlando. Uh, Before that, I served as assistant professor or in various capacities like assistant professor, instructor in three different universities in Turkey, that University of Uzin and Bilkent University. Uh, and previous to that, I was working as a lecturer in NUFAST, which is a university in Islamabad, capital of Pakistan. So I did also some industrial internships during my PhD studies in like Ireland and Spain and Sweden. Okay, so that was like very brief information about myself, and now let's focus on what is this course about, CSCI 2230, right? Uh, so let me give you a very brief and simplistic course overview. So to understand or to just get an idea of what we are going to talk about in next 4 months almost, consider like you have a miniature computer. So when we say miniature computer, which we means like uh, you have all different components which are needed for any meaningful computation. So you have CPU. Uh, So you have central processing unit, which is responsible for executing your instructions, right? And then you have a kind of memory, which is responsible for only holding your program, which is executed by your CPU. And then you have another different kind of memory, which is named as RAM. And this memory is responsible for holding the data. Definitely, when you are running the program, so your program consumes some data and generates some more or new data, right? So the data which is supplied to your program, it comes from the RAM, and then the data which is generated by your CPU as a result of executing the program is stored back into the RAM, right? And then you have another form of memory, which is known as electrically erasable PROM, programmable read-only memory, right? So we are not going to here talk about what is the like how it is different from RAM and why we have different kind of memories like flash ROM, RAM, EEPROM, right? But here we are I just want you to get the idea that you have a miniature computer which is on a single chip, right? And all the different components of that computer are contained on that single chip. So your CPU, your different kind of memories, you have timers, you have interrupt units, ports which are responsible for interacting with the outside world, right? And your clock source, which actually enables your whole computer, right? And other peripherals. So everything is on a single chip. So this is different actually from what you have in your regular computers. Like by regular, I mean the computers which you have in form of desktops or laptops. Because in all those computers, what happens is like you have these different components on different chips, right? You have a separate chip which holds only CPU, and then you have a separate chip which may hold only RAM or random access memory, and then maybe there will be a separate chip to interact with the outside world, like for example, different kind of devices. So what happens is that in those desktop in your laptop, you have multiple chips, and then those chips are connected together through buses, right? But this is different from what. But here in this course, we are going to consider a miniature computer where everything is on a single chip. So that is main difference. So this miniature computer, it doesn't have any system level software, which means that it doesn't have an operating system. Uh, so, uh, because why we don't have a operating system? Because everything is on a single chip, and the RAM which you have, it is so small in size that you cannot place or it is not able to hold a operating system, right? So you don't have enough memory. So it is not possible to support an operating system or supporting the execution of an operating system on this kind of miniature computer, right? So if we don't have operating system or system level program, so we still want to make use of this miniature computer, so we need to do the bare matter programming. Bare matter programming basically mean that we first study the hardware or the internal details of this single chip, how these different components are connected with each other and how they interact, and what are the internal details, and then based on that knowledge we write the program. So, we write basically that program in assembly language, right? So, assembly language, if you are not aware of what assembly language is, so as you know, your hardware or any digital hardware, it doesn't understand anything but only zeros and ones, like binary codes, right? So if you don't have operating system, so it's mean you don't have support for programming infrastructure, like for example, you can not run a integrated development environment on top of this miniature computer, right? So which means if you can't do that, so then you need to, as I said, you need to first understand the internal hardware and then program in terms of like bits, what should be the value of each bit, zero or one. But that is like very time consuming and very, very difficult to do. You can do that, but it is like very error prone and also time consuming. So that's why what people do is that they developed this piece of software called assembler. So what you do is that you can write your program in assembly language. So assembly language is not as hard as like writing the machine code in terms of zeros and one, and it is not as easy as high level language like, for example, C++ plus plus or Java or Python, right? So it is something in between. So it is somewhat human readable, but as not as human friendly as high level languages, but not as difficult as writing the program in machine code. So another thing about this type of kind of miniature computer is that we cannot run multiple programs or multiple processes on this platform at any given time at the same time. Why? Because if you need to run the multiple processes or applications on a single computer, let's say, even for example your desktop computer. So in order to support that, you need to have the operating system. Since we cannot support the operating system on this kind of platform which we are going to discuss, so in this course, so we cannot this platform cannot support multiple processes running at the same time. So which basically mean that we can execute only one program at any given time on this kind of miniature computer. So the CPU here, it is not general purpose, which means that it can be used to perform only specific tasks. Like for example, uh, you cannot like use this CPU to run, for example, let's say your X social media app, or your like, I don't know, Facebook or Instagram or something, or for example, word processor. You cannot run. Why? Because one thing is like these kind of applications, they need some services which are made possible only through running the operating system, and we cannot do that. One thing, and second, as I said earlier, the memory size is so small that these general purpose applications they do not fit into the memory. So if that is the case, like for example, if there is no operating system, and then how we can program such a system, and as I briefly mentioned it earlier, that we need to do the bare metal programming, right? So we do not have compiler support. Uh, so we need to program this hardware in assembly language, and this requires understanding of how our hardware processes numbers, right? Because whenever you are going to write the program, you will definitely be using numbers in your program, like most of the time you will be using numbers in your programs, and not only numbers. Either you will be using numbers, or you will be using some text, or which basically mean characters. You will be using some data structures, you will be using some algorithms, right? So if this kind of platform has no support for operating system, no support for compiler, and we can write program only in assembly language. But in order to write the assembly language program for any kind of this kind of platform, you need to first understand its internal architecture and its internal detail. So, for example, which means how hardware processes these numbers, what are the internal details of CPU, how many registers are there, what is the purpose of what are the purposes of those registers, and also you need to understand the characteristics are features of the all on-chip peripherals, for example, RAM, ROM, timers, interrupts, and so on, right? So this is what we are going to in our whole course will be basically just addressing just trying to understand this miniature computer, and then we will be spending 1 or 2 weeks for each of these components. For example, spending 2 weeks on understanding CPU, what kind of instructions it can execute, how those instructions are executed, what are the meanings of those instructions, how we can write those instructions in assembly language. Similarly, spending time on understanding timers, spending the IO ports, our interrupt unit, and so on. Okay. Now that is the what we saw in the previous slide. As I said, we had a single chip, and that single chip contained all the components of that miniature computer, right? But here in this slide, I'm trying to give you a brief and simplistic overview of another course, which is 41220. Basically, it is operating systems one, right? And why I'm doing so, to give a contrast or to compare with the previous figure, right? So here in this figure, if you see, again, we have different components and they are represented by these rectangles, right? For example, you have CPU, you have disk controller, you have USB controller, graphic adapter, memory, and so on, right? And but now each one of these components, they are a separate chip on their own. Like CPU is chip A, disk controller is chip B, memory is chip E, and so on. And then all these chips are connected together through system bus, right? So here our system is consisted of multiple chips, and then those chips are connected with each other. So that is the main difference as compared to what we have seen in the previous slide, right? So if we have this kind of system, which we not typically have in our desktop computers and laptop computers, so if we have that kind of system, now it is possible for us to run multiple applications on the same computer or the same platform at the same time. So for example, let's say you have two different apps, a text editor app and web browser app, and both running at the same time. Now, if both are running at the same time, each one of them for their execution require multiple resources like memory, CPU time, and access to the input or output devices, right? For example, if you are running a text editor, so when you first, in order to execute the text editor application, you first need to store its source code of that application in the memory, right? So it's mean that you need to have enough, a sufficient amount of memory in order to run the text editor application. Not only that, you also need to allocate the CPU for the execution of that source code of the text editor, right? And once it is running, then it will also be interacting with the input and output devices. For example, when you are typing, so on your keyboard, so your program will be reading some characters from the keyboard, right? And then those characters will be displayed on your output, which is like screen of your laptop, for example, right? So similarly, if now let's say you are running text editor and the web browser at the same time, the same statements are also true for the web browser. It will also need memory to store the source code of the application. It will also need the allocation of the CPU to be executed so that the source code can be executed. And this time, maybe the inputs and outputs, they are different. For example, maybe input is just clicking and output is displaying something or a new web page on your screen, right? So what does it mean? It means that these two applications are now competing with each other for same kind of resources like memory, CPU, and CPU time and input output devices. So which means that we somehow need to manage the resources among them. So it's not easy, right? So first thing is that even before addressing the question of how we can manage these resources among multiple applications, we first need an abstraction to represent the application itself in the world of digital computing, right? And then if once we have the abstraction to represent an application, we need to manage those applications. And when we say manage, it means like managing the resources which are needed for the execution of those applications. So for example, if you have multiple processes and they need to access the same memory location, then what should we allow them to access the same memory location at the same time or not, right? So what if, like, for example, one of those application, it tries to access the private data of another other application, or if one application is allocated the CPU, but then it never releases the CPU, so like not letting any other application to execute, right? So how we can handle these different kind of situations? So all these questions, or all these concerns, they are addressed as different functionalities, are different responsibilities of the operating system. So again, here our focus is not operating system, because this is not the course about operating system. Why I placed this slide here? Just to let you understand that in this course, what we are looking at is we will be looking at a microcontroller, which is basically a miniature computer on a single chip, and it doesn't have support for the operating system. It cannot run multiple processes or multiple applications at the same time. So there is no question of managing the resources among multiple processes, because there is no such thing as multiprocessing or something. Okay. Any questions so far? Okay. So by the end of the this which will discuss, they are only applicable to at mega 3 to 8 bit. That is not true, because it is just like, for example, if you learn the C language, and you know how to write a program in C, then it is very easy for you to quickly learn C++, plus plus, or for example, let's say Java or Python, because basic constructs are same, but then every language has its own additional features, which makes it distinct from the other languages. In the same way, if you learn the internal architecture of one microcontroller, so it becomes quite easy for you if you need to move to another microcontroller. Could you repeat that again? You froze for a moment. Okay, at what point you missed me or you lost me? Ah, okay. Okay. Yeah, I will do that, but before that, let me answer this question. Will there be a lab today? No, there will be no lab today. I will make an announcement, okay, after the lecture. There will be no lab. Okay, so yeah, so what I was saying is the following, that by the end of this course, what we expect is that students are able to understand the architecture of a microcontroller, specifically the microcontroller which we are using in the course, that is at mega 3 to 8p. However, it doesn't mean that the topics and different concepts which we are going to discuss, they are not applicable to other microcontrollers. So you can understand this by just considering, like, for example, if you know a programming language like C or C++, uh, if you have already learned one language, programming language, it is relatively easy for you to migrate or to move to another language, for example, let's say Java or Python or something else, right? Why? Because the basic constructs of all these programming languages are same. However, each programming language has its own special features, which makes it distinct from the other languages, right? So same is the case for the microcontroller. So we are going to focus on our use the at mega 3 to 8p. But if, let's say, in future you want to use some other microcontroller, like let's say 8051 microcontroller, then from the Intel, then it will be very easy for you relatively to quickly learn and understand 8051 and start programming it, as compared to a person who has no previous knowledge of microcontrollers at all. So you should be able to, by the end of this course, to understand the architecture of microcontroller and the interconnection between different components. Uh, Also, we will focus on discussion of signed and unsigned numbers. Remember, we said that when you are writing the program, basically what you are doing is that you are using uh, uh, like when you are writing program in some high level language. So what you are using? So yes, I know you are using some data structures and algorithm, but data structures and algorithm, what they are processing, they are processing the data, and data is in form of what? Either it is number or it is text, right? So how we actually present numbers and how we store them, and what is like different types of those of the numbers like signed and unsigned, and then how we can perform different operations like bitwise operations. We will also cover branching instructions, which are basically used to implement if-else kind of programming constructs in the assembly language. And also we will cover the status register of the microcontroller. Uh, the microcontroller, actually any CPU, and not necessarily microcontroller, even if you have general purpose CPU like some Intel processor, they try to access the data from the memory, and for that purpose they have different addressing modes. So in this course we will also cover addressing modes, for example immediate addressing mode, direct, indirect, and so on. Uh, At the end of the course, you should be able to map the high-level language features to assembly instructions. For example, if you are asked to convert a high-level program which is using a while loop, you should be able to convert it into the assembly language to write that while loop in assembly language. Or, for example, if let's say an if-else statement, you should be able to write it in the assembly language. Similarly, how to implement functions, how to call functions, and how to implement recursion in the assembly language. We will also have a look at we can interface input-output devices, and how our microcontroller can interact with them by executing instructions, and by deploying memory addressing and interrupts. So at the end, you should be able to write a full functional or working assembly language program for your microcontroller. Okay, so what is required? You are required to have at least C in CSCI 1720 program, or in engineering 14140. So I think you are already familiar with this statement, this requirement. If not, I mean, otherwise you would have not be able to register for the course. Uh, I also expect that you have some familiarity with higher level languages like C, C++. Why? We are not going to use any high level language code, but for example, in labs or in exams or in quizzes, but in lecture slides, we may have some snippets of higher level language level language code, uh, just to explain, for example, how a while loop works or how a for loop works and so on. In lecture location. So, I mean, the lecture will be conducted on online. The Zoom link is available on the syllabus page. It is I also placed just here the link in the slides. Classes, as you know, they will be on Mondays and Wednesday from 9 a.m. to 10:15. Lab location, it is Science Hall 118, and there are two sections. Section A is on Mondays, so, but timing of both are like same, like days are different, but the timing is same from 5 to 6:50 in the evening. We have one teaching assistant. Uh, Her email is available here, also mentioned on the syllabus page of the course at the Canvas. Office hours, they are not yet decided, but I will update them on the syllabus page. Hopefully, if not today, then by tomorrow. I'm waiting, just waiting to uh, hear from her. Okay, so here we have this tentative schedule of our course. Uh, So I don't want to go through, like, definitely it doesn't make any sense to go through like each row of this the table, but the point here is like one thing, this schedule is available on the syllabus page. Second, I will try to follow this schedule as closely as possible, but then sometime maybe there will be some variations. Like for example, let's say if here I'm saying lab 2 is due on uh, 25th of Feb, right? So, but if there is, if I need to deviate from this due date, like let's say if I'm moving it up or down, so I will let you know in advance by making an announcement on the Canvas page. Okay. Okay, yeah, and one more question, one more point. Actually, today also a student asked whether there is a lab today or not. So uh, you don't need to send me emails to ask whether there is lab or not. So for example, how you can find whether today you have lab or not. So just look at the syllabus. So if, for example, it says when is this lab due? Lab due by 11:59 of which date? Uh, 4th of Feb, right? So uh, in that week, you can go, and lab is always like reserved for you, right? In those timings, like Monday and Wednesday from 5 to 6:50 p.m. So TA will be there. Uh, so on the due date, you can go and you can show the work, or even before the due date. For example, uh, on this date, the lab is not due, but the lab room is already reserved for you. So if you want to go and work or do anything related to the course, you can go and use the lab space. Okay. But when you say whether today we have the lab or not, if you mean that is there something due today, so you can check it by looking at the table, right? Here, lab 1 is due on like 4th of the January, lab 1 is due on 4th of January, and lab 2 is due on 25th of the 25th of the February, not January, sorry. Okay, so assessment policy, we will have uh, like 5 different assessment items: weekly quizzes, homework, labs, midterm exam, and the final exam, right? So, uh, so these weekly quizzes, they will be on Wednesdays, and when they are when you have those quizzes, you can again check from this table. So here it shows you that weekly quiz, the first weekly quiz 1 will be on 28th of January, right? So, but all of them are on Wednesdays, and they will be conducted in last 10 minutes of the Wednesday class, right? So in total, we will have 12 weekly quizzes, but we will count best 10 out of those 12. And each, is attendance required for lab, or are we still able to submit the assignment for full credit without going? No, you need to, it is not about your attendance, it is about showing your work to the TA. So go to the lab and show what you have done to the TA, because maybe then TA will ask you some questions to verify your understanding of the topic, and then accordingly give you the points. So it is more about showing your work and not about attendance. Okay, so I was talking about weekly quizzes. So you will have in total 12 weekly quizzes, and we will count best 10 out of those 12. And the total percentage for 10 quizzes will be 15%, which basically mean that each quiz has 1.5% weightage. Homework, again, you will have 12 homeworks, and we will count best 10 of them. So in total, you have 10% of the weightage for the homework. So which mean that each homework carries 1% weightage. Labs, there will be 10 labs, and all of them will be counted. So there is no, like, how to say, flexibility. So, and the weightage assigned to labs is 25%. So which means that each lab carries 2.5% weightage of the total score. One midterm exam, one final exam. So midterm has 20% weightage and the final exam has 30% weightage. Any questions here? Everyone is clear on assessment policy? How will quizzes work since our lectures are online? Yeah, quizzes will be online also. They will be conducted on Canvas, but they will be conducted in last 10 minutes of the Wednesday class. Okay. Anything else? Okay. So study material, we are using this textbook, AVR microcontroller and embedded system using using assembly and C. You can here I have given you the link, Amazon link for the book if you want to buy it. Otherwise, I mean, I haven't bought it. It is you can easily find it in PDF form on Google and use it. Okay. I don't know how much ethical that practice is, but it is available in the PDF form on Google. Lab requirement in lab, we will be using an Arduino kit, Arduino board kit, Arduino UNO R3 kit. You need to buy, each student need to buy it for him or herself. I have provided you the Amazon link here. It will cost you something around $50. So place the order as soon as possible so that it is shipped to you before the first lab, right? One thing you can do is the following. Uh, there are students who took this course before you, like in previous semester or before that. Maybe you can contact them and ask them if they are not using their kits anymore. You can get their kits, or maybe they can sell you in a much lower price as compared to what you can get from Amazon. Another thing is like this time we will be doing labs in groups of two students. So I don't know. I mean, I'm not asking you that everyone should buy his or her own kit, but it's up to you. I mean, if you're working in a group of two students and you think like one Arduino board is enough for you, it's fine. It's fine for me. I mean, uh, because you will be working in group. Okay, so it's not a requirement that every person should have his or her own Arduino kit. Okay, weekly quizzes. So remember we said that we will have 12 weekly quizzes. Uh, all of them will be administered online. Okay, during final 10 minutes of the Wednesday class. And also each quiz will assess the material covered in class on Monday of the same week and the Wednesday of the previous week, right? So for example, if you let me show you the syllabus. So here, for example, here you have quiz 2 here, right? So it is on Wednesday. So, but this quiz 2 will assess the material which is covered in the previous two lectures, which is basically means the Monday of the same week in which you have the quiz and Wednesday of the previous week. Okay. Uh, Labs. This is different from the last offering of the course. This time we are doing labs in group, and in each group we have two students. Uh, but if there is like, let's say, if you cannot find any, let's say, total number of students in the class, or let's say a odd number, so then maybe a couple of groups can have three students, right? But for that, you need to first get my approval. Okay. Labs, lab work will be graded as a whole, which means that all group members will receive the same score. So we will not grade or assess your work on the individual level. So if there are two students, both of them will get the same score. So this will also like uh, it is also meant to uh, motivate one student of the group, yeah, every one of you to put your best effort in the lab work, because if you are not doing so, then you are not only hurting yourself, you will be hurting your group member. Okay, and how we are going to make the groups? So for that, I have created an online sheet. So you can go there and you can sign up to make the lab groups. I have given you the link here, and this link to this sheet is also available on the Canvas syllabus page. Okay, but this sheet will not be editable after 28th. So make sure that you sign into you go to the sheet and form your groups before 28th of this month. Any questions? Okay, midterm and final exams. So, midterm exam, it will assess only the material covered by the exam date. Definitely, I mean, it's kind of understood. The final exam will be comprehensive, so it will be covering all the material presented throughout the course. However, the greater emphasis will be on the material which is covered after the midterm exam. So 70% of the total weightage will be assigned to the material which is covered after the midterm term exam, and remaining 30% will reflect the material covered prior to the midterm exam. Okay, but still it will be comprehensive, like it will cover everything. You will be responsible for all the topics covered. There will be no makeup or retake of quizzes, homeworks, and exam, except in case of unpredictable life events. So, like if you wake up late and you are not able to attend the, let's say, lecture, and as a result you miss the quiz, so that is not a life event. Okay, I mean, if it is something which is not in your control. Regrading. Whenever we release the grades of an assessment item, you can and you think like you didn't get the grade what you were expecting, or what you think you deserve. So you can always request regrading. But for that, what you can do is that you can come to the objection session. So, or you can send us an email and give us your objection you have about grading, and then we will entertain it, right? So if you have a request for regrading, you can contact TA or instructor, whoever is responsible for grading of an assessment item. So, uh, but don't delay it. Like, for example, if let's say you think like you deserve more on quiz one and you want to request regrading, don't postpone it until, like, let's say week 8th of the semester, because it is then too late, and then it increases our work, because then we need to go back and refresh our memory and then go through all the stuff which takes time, right? So as soon as you get the grade, if there is a issue, so contact us as soon as possible. Grading policy will be letter grades will be awarded according to the uh, percentage which you will earn, like uh, how many points you earned out of 100, right? And here the grade distribution is shown. For example, if your absolute scores are from 97 to 100, you will get A plus. So, I just want to make something clear here that before assigning the letter grades, and like after calculating the absolute scores earned by each students, what I will do is that I will give zero point 0.5 extra absolute point to everyone. And the reason is that uh, I just want to help those students who are on the boundary. Like, let's say the A plus starts at 97 and someone got 96.8, right? So I just want to push those students to the next higher grade by giving 0.5. But then after you are given 0.5 extra and still you are on the boundary, don't ask me for extra because it is not possible, right? We need to stop somewhere. We cannot like give infinite amount of extra points. One more thing which I want to emphasize and make it absolutely clear that in this course we will be using absolute grading. There will be no curve grading. So which mean that uh, if for example your absolute score is let's say between 74 and 76, you will get C. It doesn't depend upon your grade will not be impacted or affected by the overall performance of the class. Like for example, let's say if no one in the class gets A, uh, and everyone the highest score high let's say the highest grade is B, I'm fine with that. I will not shift the grades up. Okay. Any questions so far? No. Okay, so if you during the course, if you have any trouble or you are unable to understand any topic or have facing some difficulty in performing the lab work, so communicate with the T or the instructor as soon as possible. Do not wait or do not postpone your issues or your questions like towards the end of the semester. I will advise you to form study groups and learn from each other. Yes, labs are required to be done in the labs, but even uh, uh, besides lab, it's better if you are like let's say if you are studying slides of a particular lecture, maybe it's better to sit together and go through them because then you can take help from each other. Also, when you are writing emails to me, please make sure they are not subjectless. Mention your name, your course ID, because I'm also teaching another course, and sometimes like students send an email without mentioning their course ID, and then I need to go to the canvas and search their name, that in which course they are registered. Takes time, right? So mention your course ID and also the lecture, quiz, project, or exam number uh, related to which you have a question or you are facing an issue with, right? As I said, you are encouraged to study together in form of groups, but not you are not encouraged to copy, which means that uh, benefit from each other in understanding the material. But when you are doing the quizzes or you are doing the homeworks, you are supposed to do them in individual capacity. Okay, any questions? Okay, so if no questions, then let me explain something which will be very helpful for you for the rest of the course. And whatever I'm going to explain here, maybe you will need to refer to these couple of slides again and again. So here we are going to talk about pin mapping from Atmega 328P chip to the Arduino Uno board. So what is Atmega 328P? So it is actually a chip which holds your that miniature computer which I mentioned in like second or third slide, right? So and what is Arduino board? Arduino board is actually a development kit which you can use to easily program your Atmega 328P, 328P processor or chip, right? So this is your Arduino Uno board, and here you have this chip, this microcontroller, right? Now the thing is, if you look that this board has its own pins, all of these pins here, right? And here also on the left side, on the right side, right? So these are Arduino Uno board pins. But if you look at the chip itself, it also has its own pins. Like, so these two pins are different. Like the pins on the board, they are naming, and the pins, the naming of the chips, naming of the pins on the chip, they are different. So the question is then, Like, how can I understand this, how this particular pin is connected? Is it connected with, let's say, the pin number 13, or is it connected with pin number 4? Is it connected with A1? How can I know that, right? And why it is important to know? Because all the material when we which we will be covering uh, in the course, it refers to the pins of the microcontroller chip. So those lecture slides, they don't talk, or they don't explain things in terms of the pins of the Arduino board. So because remember, we are focusing the microcontroller at Mega 328P. Why we are using this board? Because it only makes our life easier to program and to use this chip, right? So the purpose of the board is only to make everything easy for students, right? But again, as I said, then it raises the questions that, like in the lectures, we are mentioning the pins of the microcontroller, but in the lab, we are using this board and we are connecting everything with the pins of the board. So, what is the relationship between the pins of the microcontroller and the pins of the board, or basically how they are mapped, right? So here you see this pin diagram of the microcontroller itself. So it is 28 pin device or 28 pin chip, right? And remember, now when we will talk in, like in lectures, when we cover the different sections of the, like different sections of the material, we will be, like, for example, referring to the pin D0, PD1, PD2. But here on the board, you don't have pin PD0 or PD1 or PD2, right? So, and then when in the lab you will need to use it, you will actually need to connect things with these pins here on the right or on the left, right? So you need to know that how the microcontroller pins are connected, right? So all these pins on the microcontroller, they are actually multi-purpose pins. So what does it mean by multi-purpose pin? It means that actually you can configure these pins. How? By writing specific values in internal registers of the chip. So for example, let me give you only the example of this pin number 23, right? So you can use it as input or output pin. You can use it as analog, as an output pin of analog to digital converter. You will later in the course you will know what is an analog to digital converter and how it is used. Or you can use this pin as an interrupt pin. Okay, uh, interrupt pin 8. So, like, it has three different purposes. So for which particular purpose it is used, it depends upon how you have programmed some particular register in the microcontroller. So now let's get back to the question that how we map the pins from at Mega 328P to the Arduino Uno board. So here for that, uh, what you can do is that you can always refer to this table. So the first column in the table, it gives you the name of the pin on the at Mega 328P chip. The second column gives the name of the pin on the Arduino board to which the at Mega 328P pin is mapped or connected. So when we say, for example, here it means that PD0, it is actually connected with D0. So where is PD0? This one, right? So this is basically connected with D0. What is D0? This one here, if you can see. So this is D0 or digital zero. So D stands for digital. So, and then the third column gives you the description of the pin from the perspective of Arduino board, and fourth column gives you the alternative function. So for example, this pin can be used uh, PD0. It can be used for input or output, for reading an input or display sending an output, or it can also be used as a pin for in the serial data uh, transmission or serial data communication protocol. So, which is again as another purpose or alternative purpose of the pin, right? and it can also be used as an interrupt pin. And as I've said, how we know that in what particular time the what is the purpose of this pin, we can configure it by writing specific value in specific registers. So same is the case for all other rows in this table, that you can simply by, for example, by looking at PC0, by you can this row tells you that PC0 of the Arduino at Mega 328P chip is connected with the A0. So where is PC0? Here. So PC0, it is connected with the A0. Where is A0? This one, right? So PC0 basically it becomes, if I count from here, one, two, three, four, five, six. So one, two, three, four, five, six, this one here. So this one is connected to A0, right? So this table will be very helpful for you because you will need to know this mapping in your labs. And you can come back to it whenever you need it. Okay. Any questions? This last slide is basically the full picture of the pin mapping, but it will be very difficult for you to understand at this time point. However, towards the end of the course, when you are like most of these pins and their description and their names, at that time, if you come back and have a look at this lecture at this slide, then it will be like meaningful for you. But at this time point, you can ignore it. But once you know everything, and then in the future you need to quickly refer to the pin mapping, this figure will become very handy. Any questions at this time point? No? Okay. So before I close the lecture, before I stop, just one I want to mention this, that in the upcoming lectures or in all the remaining lectures of the course, we will also have some online polls or online quizzes during the lecture. They will not be graded. They will be only to increase, how to say, uh, your understanding, and to help you like when you will be solving those polls, or solving answering those questions, maybe then you will be testing your own understanding of the topic what we have covered until that point, and then it will maybe trigger some more questions or discussion during the class. Okay, so we will have some online polls. They will be required in the sense that all of you will be you will all of you will have to participate, but then they will not be graded. Okay, so if no questions, then that's all for now. Again, all how will quizzes will work since our lecture. Okay, I answered this question already. All the lectures will be recorded, and I will place them on YouTube and then provide you with the link through the Canvas syllabus page. Okay, so that's all for today, and then see you next week. Thank you.